Okay, so we can now start. Okay, so where we left off last week, we had a look at files and exception handling. And in today's lecture, lecture 6, we're going to look at the first part of advanced object orientation. So I've been saying this for a while. We'll do this when we get to advanced OO. We'll do this when we get to advanced OO. Now we're at the point where I can actually show you some of the stuff which I said I will discuss. So you should be paying attention to the lecture and not helping your friend. So what we're going to have a look at is, in the first part of advanced OO, we're going to look at inheritance as a plain and simple thing. Inheritance you should know or should remember from Computer Science 1B, and that is looking at a relationship that exists between classes that can inherit or get some of the information from a parent class or a superclass or a base class. All of those terms can be used interchangeably for the class that's higher on the hierarchy, more up on the list of classes in the hierarchy. So the high up on the hierarchy, it's more of a base class or a base class, a parent class, or a superclass. Then we're going to have a look at more advanced concepts, and that is to do with interfaces. And that's what we'll look at the second part in the next lecture. So for now, what we're going to look at is inheritance. Inheritance, reusing functionality from an existing class in a new class. Now, usually when we do inheritance, it's to model some sort of a relationship. And the relationship we're looking at here is a relationship. Something is something else. So that's how the relationships are going to factor in. There are other relationships. We looked at them in the documentation practical lecture when we looked at UML. There's has a, kind of, is kind of. So all of those different things, we'll have a look at them as we get to those different sections. But right now, we're going to follow along just with is a relationship. And what we have in Java, the convention that we use and the keywords that matter in Java is to use something called a superclass and a subclass. The reason why it's a superclass is because the keyword associated with accessing the base class or your parent class is called super. And that's why they use this in the context of Java. That's the name they use. Obviously, when we're talking about discussing it, you should know what is a superclass, parent class, base class, all means the same thing. It's just Java has a specific keyword for it. But if you discuss it, any of those are fine to discuss. Likewise, with subclasses, subclasses are your child classes, derived classes, based, derived, parent, child, super sub, yeah. So that's the terminology that you can use there. And to show inheritance, we have the extend keyword. So that will show inheritance. When we work with interfaces, and we'll see why we need to work with interfaces, we'll see another keyword being used in that location. Now, we sort of talked about this very briefly, but in all the Java classes that you have, all of them have an ancestor class. An ancestor class basically says it's the parent of the parent of the parent of any class. It's the ancestor of every class. That is Java lang object. So there is no explicit thing that says it extends object when you write out a class. When you wrote out the first class we wrote, when we did the Hello World example, we didn't have to write extends object. It just happened automatically. So by default, even if you don't specify anything, it's already extending one class, and that is Java lang object. So we'll talk about Java lang object. It's one of the items we'll talk about a bit later. But you can see there's Java lang, that's the package, lang being the language, Java language built into the actual language of the programming language. So when we do inheritance, we usually have subclasses that we need to create. We have a parent class, we specialize into a child class. Now, that's very important that we specialize. It should contain more information, more specific, more specialized information when we go down the hierarchy. Conversely, if we go up the hierarchy, we're going to get more generic, more abstract. Now, when we do relationships, we do inheritance, you have to be wary about when to use it and why you are using it. So the example in the slides is we have a square and a rectangle. Those are two shapes. And if we look at a square is a special case of a rectangle where the sides are of the same length. So if you have a rectangle of width and height or width and length, a square is just where those two values, width and height or width and length, are the same. Now, would you model a square as a subclass of rectangle? Well, the answer is on the slide, but would you do that? The answer is no. Why is it no? No, that's not the reason. Not anything logical like that. It's more simpler. If we look at a rectangle and we look at a square, are we gaining information down the hierarchy or are we losing information down the hierarchy? Rectangle has width and height. What does square have? Just one thing, a side, a length. So are we gaining information or are we losing information? Losing information. We went from two things to describe the thing to one thing to describe it. So we can't model that relationship because it doesn't make sense. We're losing information. As you go down the hierarchy, you want to gain information, make it more specialized, make it more interesting. The same thing can be said about things that might have similar attributes. You can't have something like a person and a rectangle having a relationship, even though both of them have a height and a width. Do you agree? People have height and width. Not everyone wants to talk about the width part. Not everyone wants to talk about the height part, but we do have that. But are all of you rectangles? Can I call you a rectangle? Can I call you a square? Is that better? Doesn't make sense. Even though the attributes are similarly named, it doesn't make sense. So don't model everything as a relationship, especially an inheritance relationship. There was a time in the years of IT gone past where when object orientation came out, everybody made everything into an object, and everything was done through inheritance. And what happened was you had inheritance hierarchies. So how many classes in the inheritance hierarchy went up to about 300 classes. Does that make sense? Having 300 classes in the hierarchy, and if you need something specific, go back in the hierarchy and figure out what's where. Didn't make sense, but because people thought, okay, this is the best new thing, I'm just going to apply it everywhere. Obviously, that's not the right answer. As I mentioned before, you've got a screwdriver and a hammer. If you've got a screw in front of you, one works better than the other. If you've got a nail in front of you, one works better than the other. You can try and use the wrong tool to do the job. It might work. It won't be very easy to do. So you have to use the tools that are right for the job. You need to understand how to do inheritance to know when to use it and when not to use it. So as we go on, one very important thing about Java, Java does not support multiple inheritance, not at all. There's only one direction. When you go up, only one parent you're going to find there, not more than one. Now, there is a way that Java takes care of the benefits of having multiple inheritance without the drawbacks of it. And that's something called interfaces. So when we get to part 2, we'll talk about interfaces and how they fit into the picture. Then, as we mentioned previously, if you have the protected keyword, that can be accessed by the class itself in any child classes thing. So if you're working with hierarchy and you need your child classes to access some information, but not everything, then you can put it as a protected keyword. So anyone outside the hierarchy can't access that, but whoever's in the hierarchy can. And then the last point there that's very important subclasses cannot reduce the visibility of a superclass member. What does that mean? It means that if you have something declared as public in a parent class, you can't change it to private in a subclass because you're reducing the visibility. So you cannot change that as you go down a hierarchy. Obviously, you can change it to make it available. You can make something private in your parent class, and in your child class, you can make it public. But you can't go the other way around. You can't reduce the visibility. So here we get to the super keyword. So the super keyword is very similar to this keyword, except now we're referring to the superclasses instance or superclasses methods, as we'll see in a moment. So when you use super, what we're trying to indicate is you want to invoke either the constructor of your superclass. So you'll say super and then pass in the parameters for whatever constructor you want. The only time you can do this is in a constructor in the child class. And then you can also invoke a superclass method. So say, for example, the superclass did some calculations. You want to extend those calculations in a method that's the same name, but overriding. We'll talk about that in just a moment. Then you can call the superclass's implementation and then call your implementation afterwards, or whichever order you need it to be. Now, what's very important to note is as soon as you have a hierarchy, by default, when you call the constructor of something in your child class, in your subclass, there is an implicit call. Implicit meaning you don't have to write it out. An implicit call to a superclass's no argument constructor. Because remember, by default, which constructor is created for you? No arguments constructor. Now that gives us a bit of a problem. What happens when we create a constructor? What happens to the no arguments constructor? It goes away. As soon as you create a constructor, there is no more a default arguments constructor. So that means the superclass cannot call, you cannot call the superclass's no argument constructor, because if you define one, there is no arguments constructor. So there's a little example of code right at the bottom of the slide, only 5 lines long. But even though it's a very short amount of code, there's a lot of problems going on there. So this code will not compile. We have a hierarchy of 2 classes. We have a class called fruit, which has a constructor which takes the string. What the constructor does doesn't matter. What the class does doesn't matter. All we're focusing on is we have a constructor for our parent class. If you look at the child class is called apple, extends fruit, and no other code written for that. This code doesn't compile. Why? I just told you the answer before I talked about the question. So what is the problem? I know you know. So in the constructor for Apple, it provides us with a default constructor because there's no constructor in Apple. The only constructor that the default constructor knows about is the default constructor in the superclass. Is there a default constructor in the superclass? No. Which constructor is there? One that takes a string parameter. So you have 2 options to do a fix here. What are your 2 options? Seems like only one person wants to pass the test next week. 1 or 2 people. So one option is to create a constructor in Apple that calls the fruits constructor, because we need that to work. We need that relationship to connect that way. That's one option. What's the other option? You could remove fruits constructor, but there for probably a reason. So maybe you don't want to remove it. We could add a no arguments constructor to the fruit class. That's the other option. Now, it might not make sense to do that, but that is a possibility. You can add a default no arguments constructor. Removing constructor is probably there to initialize some variable, so you probably don't want to remove it. And that's the same reason why we might not want to do a default constructor, because what are we going to initialize the value to? In this case, you might say, okay, that string might be the name or the variety of the fruit that's getting initialized, but we don't know. You're assuming things because we don't have the whole picture. We're just trying to illustrate the problem here. But when you're actually developing your own code, you need to figure out, depending on what your circumstances are. Everything, as always, it depends on what you're trying to do. So overriding methods and casting. So overriding, we talked about overloading. Overloading is when we have the same name in the class with different return types, different parameters. So that's overloading. In the same class, same name, different return type, different parameters. With overriding, it's the same name, same parameter, same return type as your parent, but you provide different implementation. So not going to show you that we'll see when we get to the tutorial code. What I want to talk about is some things where we can look at preventing overriding and subclassing. This is where we see another use of the final keyword. So final, we saw before when we use the variables to indicate constant values, values that don't change over time. What we can also do is put final onto the modifiers for a class. That will indicate no child classes can be created for that specific thing. If we put final onto a method, then that method cannot be overwritten in any child classes. Now, why would we want to do that? So if you're looking at a full class, why would we stop someone from creating subclasses of a full class? Why would you want to do that? You don't, no comments. I thought you had a comment. No one?
Well, if you have a final class, like you are creating this for a class like car, and you have subclass type of car, why would you then want to have subsets of that type? It's finally always going to modify.
So if we look at the hierarchy and it doesn't make sense to go specialize any further, we can stop that from happening. So one reason why we can do that, and you can sort of see it here with the next class, is for security reasons. So here there's an example. Obviously, I can't show you full source code for stuff because that's too much code to fit on the slide. But think about a hypothetical situation where you have a class that handles security. Either it's going to do a login function to access a system, a login function that eventually is for a front end of a website, a front end for an app, something along those lines. And in order to bypass your system, the person who wants to compromise your system, I don't like to use the word hack because hack means a lot of different things. The person who wants to compromise your system, all they go and do is say, okay, you got this class called security system, create the subclass of that and inject that into the code. And that subclass, for that login function, all it does is it returns true. It doesn't do any login functionality. It doesn't check usernames, password, doesn't care, just says true. There you go, system is compromised. So one way to stop the person from doing that is to indicate that this method cannot be overridden in any child classes. Doesn't solve your problem of your system being compromised in other ways, but at least you stopped one thing.
In that example, where you have a class security system, because there's only one method that's considered final, would the compiler not optimize your class and just consider the class final?
No. Well, no, it wouldn't do that necessarily. Because you can still add other methods in child classes. So it doesn't stop that or optimize it in any way like that.
So we have a final class, then consider it an useful class.
Sorry, just repeat again. I didn't quite get.
So if we have a class using the final keyword, is it then considered a useful class? Then it can't be overridden.
So a final class is separate from a mutable class. A mutable class needs to have those three things we talked about earlier when we talked about object orientation. no public accesses, mutators, no, all information must be private, and that accesses mustn't return a reference to a mutable data type. That's regardless of whether it's final or not. So don't confuse the two. Immutable is one thing, final means something else.
So what would be the difference in effect between having a final method and static method?
Okay, so what is the difference between having something as a final method and something that is a static method? Static says that there is only one instance in memory that uses those things. It's the class that's available in memory that we can use. When something is final, it belongs to an instance, and that instance indicates that any child classes cannot override that specific functionality. So again, two separate keywords trying to do two different things. Okay, moving on to the next session, talking about casting. So with Java, there is something called auto boxing and auto unboxing. And that's just a fancy way of saying that certain places there is casting done for you automatically, and some places where you have to explicitly cast. If you're going up the hierarchy, so you're going from a child class to a superclass in terms of variable declaration, you don't have to do any casting. If you're going down the hierarchy, you have to do casting. So the example there you can see on line 1, implicit casting, because I'm going up the hierarchy, no problem. A circle can be stored in an object reference without an issue. And note there, object, we don't have to import anything because it's part of built into the language. We can just put a reference to object there. If I want to change that back to a circle, I have to explicitly cast. So I have to ask the compiler to please change this reference to a circle. Now, what problems can occur? What if the thing I'm trying to change to a circle is not a circle? Then I get an exception. If I try and change something to something it's not, we get an exception. So there is a way, remember exceptions are very expensive, we don't want to use them if you don't have to. There is a way we can test if something is a circle, or any other class for that matter, and that is the instance of keyword. So that keyword instance of will test and see, is this reference, in this case on line 5, that reference O, is that a circle? If it returns true, then we'll do the true part, otherwise we'll do the false part. Obviously the false part not on the screen, but it will do the appropriate things. Now, there is a better syntax for this. You can see on line 7, there is a cast that has to happen there. With, I think it was Java 15, there's a shorthand we can write. We can skip that line 7 and then just put the reference for C in that instance of statement. And that, I'll show you an example when we get to the tutorial. Now for Java Lang object, there are a lot of methods. And again, if you want to see all the methods that are available in Java Lang object, you can look at the Java documentation for Java Lang object. The two that I want to point out now are toString and equals. ToString provides a textual representation of a class. Now, the implementation in the object class tells us the canonical name, and canonical name is the full name, so package name, class name. Then it shows the @ symbol and then a hash code. That hash is a hexadecimal representation of the hash of the class. We can change that implementation. There's a hash available in the class itself. We can override that. But most likely, what we'll do is we'll override the string method to return information that's useful for us. We can override the toString implementation to perhaps put out useful information. So for example, for the student, we might want to put out the student number. For your drone class, or sorry, not drone, the telescope class, you might want to put out the ID and some other information. We can write all of this in the toString of that. So if we call system out println and then an instance, it will use that toString and print out something useful instead of some random numbers which don't make sense. The other method that's useful to have here as well is equals. Remember, double equals, if you're typing double equals, that's comparing memory references. The equals method compares whatever information is inside the instance. By default, equals returns memory reference equals. But we can change this. We can say, for example, if the IDs of two exoplanets are the same, they're the same exoplanet. If the IDs of two students are the same, they're the same student. If the IDs of two modules are the same, they're the same module. We can override that to make sure. We can do something complicated. We can say, take the codes, take the name, take everything, and take all of that. Only all of that is the same, then they are the same instance. So you can override these methods and change them to suit your needs.
You have two identical strings of string, and they're identical only in the value, but one has been created with a new keeper, so it's its own thing within the string. Well, equals return true, try to wait it. So one normal string and one string created with new, they're the same.
Okay, so the question was about two strings using intent strings. One is created with a new constructor, one is created normally without a constructor. Will equals return the equality of the strings or equality of the references? Because string is a class and it can change the functionality is changed to do equals on a character comparison. So even if they're created differently and they have different references, we're looking at the actual internal structure of the strings, and they'll return the same. If they're the same, they'll return true. So we can change that. We can have our own class and change how that works. If you want to, you can perhaps write an optimization where you can say, check reference equality first. If reference equality gives true, we don't have to calculate all the rest of the stuff. You can write something like that if you want to. So here is a little example of inheritance, and there's a small inheritance hierarchy here. You can see there is a parent class called geometric object. It has some attributes there, color, fold, and date created. Now you'll see here, even though we say that UML is supposed to be language agnostic, which means we don't have to specify or try not to specify. If we're using things that are in the language to describe something, then you can put those things in. So for example, the color comes from JavaFX. Remember, I told you JavaFX is the user interface tool we'll be using in the future. And you can see there is a class they call color. So that represents color in JavaFX. Then there is date, and you can see there Java util date. That's how you represent a date. Then there's just a constructor and not much else. Then we have two subclasses, or two child classes, two derived classes, circle and rectangle. And then you can see circle has a radius, and then constructors that take in no arguments, and then one which takes in the arguments, and a couple of methods there, area, perimeter, diameter, and a print method. And similarly, on the other side, rectangle has its own things with a height constructor that takes arguments, and then area, perimeter, and print rectangle. So there are some things that are common between the two. You might want to try and make those things correct, but let's just look at the example as we have right now. So here is a class for my geometric object. You can see there we're importing the things that are relevant because we need to use them in our code. So there's the imports for JavaFX for the color and Java util for the date. 5, 6, and 7, that's where we initialize our instance variables. So there you can see we initialize our color to be white by default. The Boolean is, if it's filled or not, is false. And then the date created is whenever you create an instance, that date will be initialized to the current date and time. Because it doesn't fit all on the screen, I took out the access and mutator methods, but there'll be an access and a mutator method for each one of those things. And the interesting thing here is the toString method. So we're overriding the toString method to return a customized string. What's wrong with this already? There's something wrong with this example. How about I don't give you the answer and I'll ask it in your semester test next week? That sounds like a good thing to do. Okay, so this string method returns a string that indicates the things inside of there. So it will tell you when it's created, what's the color, and is it filled or not. If you look at the circle class, again, some of the methods are not there because it won't fit on the slide. But there you can see there it extends geometric objects. So that's how we indicate the hierarchy extends. And then we have the radius declared as a private thing. Then we have circle, no constructor, no arguments constructor, circle with a radius. And note there, for that radius, we actually call the mutator method to set the radius. Then we have get area, get diameter, get perimeter, print circle. And print circle, all it does is print the current instance on system out print line. It might be the case that someone wants to print it somewhere else. So that's one way to just call it very quickly. We could print it somewhere else. And if you look at the toString method there, you'll see there on line 13, it calls super.toString. So call the implementation of the parent class, create that string that gets returned, and then append on my extra information, which is the radius information. So when we print out toString for a circle, it'll print out date created, is it filled or not, and the color. And then additionally, it will print out the radius. So similar things happens with the rectangle. Again, some of the methods are not there, access and mutator methods, because it won't fit on the slide. But there you can see there, get area and get perimeter using those specific things. There should be a toString as well, but I didn't think it will fit on the slide, so that's left out as well. So that's a basic example. I can see there are some things that we can sort of try and put together into our parent class. Maybe things look similar. Maybe you want to enforce that certain methods need to be implemented in our child classes. And that's something we'll look at when we get to the next lecture, part 2 of advanced object orientation, when we look at interfaces. All right, so even with problems, we seem to have completed our lecture. That's good. So if there are any questions, I'll be in the front. Otherwise, I will see you all tomorrow for practicals. Just 1 minute. Okay, so the scope of the test is in the learning guide. There will be a notice on Eve as well. Yes, there is an override missing. We need to talk about that still. And the attendance code is right at the top, but I see some people repeating it. All right, so I'll stop the recording now.